You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Speech recognition is the process of converting spoken language into machine-readable text. It allows computers to listen to human voices, break down sound waves into components, and map those components onto words and sentences. Unlike written text, spoken language comes with variability in pronunciation, accent, speed, and clarity, making recognition a far more complex task. Yet it is essential for enabling machines to understand and respond to human speech naturally. Speech recognition powers transcription services, virtual assistants, and dictation tools. It provides accessibility for those who cannot easily type and enables hands-free interaction with devices. By bridging the gap between human speech and digital text, speech recognition expands the ways people can communicate with technology, transforming it from a passive tool into an interactive partner capable of engaging in dialogue. Speech generation, often referred to as text-to-speech or TTS, is the complementary process of producing natural-sounding spoken output from written input. While speech recognition allows machines to listen, speech generation allows them to speak back. This technology makes written content audible, supporting accessibility for visually impaired users and powering applications like voice-enabled GPS systems or audiobooks. Early systems sounded robotic, with flat tones and mechanical pacing. Today's advanced models create speech with rhythm, intonation, and expressiveness that closely mimic human voices. The ability to generate convincing spoken language makes machines more approachable, enabling smoother human-computer interaction. Together, recognition and generation form two halves of a loop that allows machines to participate in spoken communication, turning them into conversational agents rather than one-way tools. Early approaches to speech recognition relied on simple techniques like template matching and rule-based systems. Template matching compared incoming speech signals against stored examples, recognizing words only when they closely matched predefined patterns. This limited recognition to small vocabularies and clear speech. Rule-based systems attempted to encode the structure of language into logical rules, linking sounds to words based on phonetic features. While innovative for their time, these systems lacked flexibility and struggled with variability in human speech. They could recognize isolated words, but faltered in continuous conversation. These early methods highlighted the challenge of translating the fluid, ambiguous nature of speech into rigid machine rules. Their shortcomings motivated the shift toward probabilistic and statistical models that could handle uncertainty more gracefully. Acoustic modeling became a cornerstone of statistical speech recognition. It represents the relationship between raw audio signals and the phonemes, the smallest units of sound that make up spoken language. Sound waves are captured, converted into features like frequency spectra, and then mapped onto likely phonemes. For example, the S sound at the beginning of speech has a distinctive spectral signature that an acoustic model can identify. By breaking speech into these atomic units, machines can build words and sentences piece by piece. Acoustic models acknowledge that speech is variable, representing sounds not as fixed templates but as probabilistic patterns. This flexibility allows recognition systems to handle different voices, accents, and pronunciations, making them far more adaptable than earlier template-based approaches. Language modeling adds another critical layer to speech recognition by predicting likely word sequences. While acoustic models determine what sounds are being spoken, language models interpret them in context. For instance, if a system hears a sound that could be there or there, the language model helps choose the correct word based on surrounding context. A phrase like, "they went to their house," is more probable than, "they went to their house." Statistical language models used probabilities from large text corpora to guide recognition, while modern approaches rely on neural networks to capture deeper patterns. Language modeling brings recognition closer to comprehension, ensuring that transcriptions are not just phonetically accurate, but also linguistically meaningful. Hidden Markov models, or HMMs, dominated speech recognition for decades. HMMs represent speech as sequences of states, each corresponding to a phoneme or word, with probabilities governing transitions between them. This framework captures both acoustic variability and sequential structure, allowing systems to model the flow of speech over time. HMMs proved effective for large vocabulary recognition and were used in many commercial systems before the deep learning revolution. Their strength lay in balancing structure and flexibility, but they also had limitations. They often required simplifying assumptions and could struggle with complex dependencies in speech. Nonetheless, HMMs paved the way for modern systems, demonstrating that probabilistic models could successfully manage the uncertainty inherent in spoken language. The transition to deep learning brought dramatic improvements in accuracy and naturalness. Neural networks replaced traditional HMM-based pipelines, learning representations of speech directly from raw data. Convolutional and recurrent architectures captured patterns in audio, while end-to-end training allowed entire recognition systems to be optimized together. The leap in performance was striking. Error rates dropped significantly, and systems became robust to variations in noise, accent, and speaking style. Deep learning allowed recognition systems to scale with data and compute, transforming them from specialized tools into mainstream technologies embedded in everyday life. For learners, this transition highlights how a single paradigm shift can redefine an entire field, pushing capabilities from good enough to broadly usable. End-to-end speech models exemplify the deep learning approach by mapping audio signals directly to text outputs without intermediate steps like phoneme decoding. These models, often based on sequence-to-sequence architectures with attention or transformers, learn to align input sounds with written words. For example, a spoken sentence can be converted into text in one streamlined process rather than passing through separate acoustic, phonetic, and language modules. End-to-end models simplify design, reduce error propagation, and achieve remarkable performance, particularly when trained on massive datasets. They also enable multilingual recognition more easily, as the same architecture can adapt to different languages. End-to-end systems represent the modern standard, showing how deep learning consolidates complex processes into unified, efficient solutions. Speech recognition can operate at different levels of granularity, ranging from phonemes to whole words. Phoneme-level recognition focuses on the smallest sound units, assembling them into words through language models. Word-level recognition, by contrast, attempts to recognize entire words directly. Each approach has strengths and trade-offs. Phoneme recognition is more flexible, handling new words by recombining known sounds, but it requires strong language modeling to resolve ambiguities. Word-level recognition can be faster and simpler in constrained vocabularies but may fail when encountering unknown terms. Many modern systems blend these approaches, balancing flexibility with efficiency. This layering illustrates how speech recognition, like language itself, operates on multiple levels of structure simultaneously. Text-to-speech systems developed alongside recognition, enabling machines to generate spoken language. Early methods used concatenative synthesis, stitching together small recorded speech segments to form words and sentences. While intelligible, these systems often sounded robotic, with awkward transitions and limited flexibility. Parametric synthesis offered more control by generating speech from models of vocal parameters, but the results often lacked naturalness. Both methods were important stepping stones, showing that machines could speak, even if imperfectly. They set the stage for neural approaches, which would later produce speech with far greater fluidity and realism. These early methods remind us that progress often comes in layers, with each generation building on the lessons of the last. Neural text-to-speech systems marked a breakthrough in natural-sounding voice generation. Deep models such as WaveNet and Tacotron moved beyond stitching segments, instead learning to generate audio waveforms directly. These models captured subtle aspects of speech, such as intonation, rhythm, and timbre, producing voices almost indistinguishable from human recordings. They also offered flexibility, allowing voices to be customized, sped up, or adjusted in tone. Neural TTS has enabled high-quality virtual assistants, audiobook narration, and accessibility tools. The difference is dramatic. Where early systems produced mechanical speech, neural models produce fluid, expressive output that feels conversational. For learners, Neural TTS highlights how advances in deep learning extend beyond recognition into creation, transforming machines from listeners into fluent speakers. Prosody and intonation modeling add another layer of realism to speech generation. Human speech is more than just words strung together. It carries melody, stress, and rhythm that convey emotion and emphasis. Modeling prosody allows machines to generate speech that sounds lively rather than monotonous. For example, rising intonation can signal a question, while pauses and emphasis can highlight key points. Without prosody, even accurate pronunciation can sound unnatural or robotic. Modern systems incorporate prosodic features to make speech more engaging and believable. This reflects the broader challenge of human communication. Meaning is carried not just by words, but by how those words are spoken. Multilingual speech systems represent an important advance, enabling recognition and generation across many languages. Traditional systems often required separate models for each language, demanding vast effort to build and maintain. Deep learning has made it possible to train multilingual models that handle dozens of languages within one architecture. These systems support real-time translation, global accessibility, and more inclusive interfaces. For example, a single voice assistant may understand commands in English, Spanish, and Mandarin without switching modes. Multilingual systems highlight both the promise and challenge of speech AI. While they expand communication across linguistic boundaries, they also demand immense training data and careful handling of cultural differences in pronunciation and expression. Noise and robustness remain key challenges in speech technology. Real-world environments are rarely quiet, and systems must handle background chatter, traffic sounds, or poor microphone quality. Accents and dialects further complicate recognition, as the same word can sound dramatically different depending on the speaker. Robust systems use techniques like data augmentation, noise reduction, and advanced modeling to maintain accuracy in challenging conditions. Yet, even the best systems can falter outside of controlled environments. For learners, robustness illustrates the ongoing gap between laboratory performance and real-world deployment, reminding us that speech AI must constantly adapt to the diversity and unpredictability of human communication. Applications of speech recognition and generation are widespread and deeply integrated into daily life. Virtual assistants rely on recognition to understand commands and generation to respond naturally. Transcription tools convert meetings and lectures into searchable text. Accessibility tools read text aloud for visually impaired users, or allow speech input for those unable to type. Entertainment systems use speech for interactive storytelling or gaming. These applications highlight speech AI's dual role as both utility and enhancer, making technology easier, faster, and more inclusive to use. By giving machines the ability to listen and speak, recognition and generation transform computers into more natural partners in communication. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Voice assistants have become one of the most visible applications of speech recognition and generation. Systems like Siri, Alexa, and Google Assistant allow users to interact with devices using natural spoken commands. Recognition systems capture and interpret requests, while text-to-speech systems generate responses in friendly, human-like voices. These assistants can set reminders, play music, answer trivia, or control smart homes. The convenience lies in hands-free conversational interaction, making technology feel more approachable. Behind the scenes, These systems combine recognition with natural language understanding, tying speech directly to actions. They demonstrate the power of integrating multiple AI technologies into seamless, everyday experiences. For learners, voice assistants highlight how research advances move from theory to practice, reshaping how millions of people interact with technology on a daily basis. Call centers and customer service platforms increasingly use speech AI to handle routine inquiries. Automated agents powered by recognition and generation can guide customers through billing issues, troubleshoot technical problems, or provide account information. These systems reduce wait times and free human agents to handle more complex cases. By recognizing common phrases and generating polite, context-appropriate responses, voice bots provide scalable support. Some systems also adapt tone and pacing to match customer needs, aiming for more natural interaction. While challenges remain in handling nuance or frustration, the adoption of speech AI in customer service illustrates its economic value. It allows businesses to extend support capacity while maintaining consistency and availability. For learners, this example underscores how speech technologies create both efficiency and new dynamics in human-machine communication. Real-time translation represents a remarkable intersection of recognition, language modeling, and generation. Speech-to-speech translation systems listen to spoken language, convert it into text, translate the text into another language, and then generate speech in the target tongue, all in seconds. These systems enable travelers, business professionals, and humanitarian workers to communicate across language barriers instantly. While translation may not always be perfect, advances in deep learning have dramatically improved fluency and accuracy. Modern systems even attempt to preserve speaker intonation, making the output sound more natural. Real-time translation illustrates how combining multiple speech AI components produces transformative applications. For learners, it offers a glimpse of AI's potential to break down one of humanity's oldest divides, the barrier of language, bringing people closer through shared communication. Dictation and productivity tools are another practical application of speech recognition. Transcription software allows meetings, lectures, or brainstorming sessions to be converted into searchable text in real time. Writers use dictation tools to compose drafts quickly, while professionals rely on transcription for accurate records of discussions. These systems improve efficiency, reduce manual note-taking, and expand accessibility. Integration with productivity platforms further extends their value, allowing automatic summarization or keyword tagging of transcribed text. For learners, dictation tools show how speech recognition amplifies human capabilities, turning ephemeral spoken words into lasting, useful records. They demonstrate the everyday utility of AI as an enabler of organization, efficiency, and creativity. Healthcare is one sector where speech technologies provide significant benefits. Doctors often use medical dictation tools to record patient notes, saving time and reducing administrative burdens. Transcription systems can capture consultations, producing structured documentation that integrates directly into electronic health records. Speech AI also supports patient interactions, enabling voice-driven symptom checkers or accessibility tools for those unable to type. In radiology, speech recognition helps annotate scans, while in nursing, it can track patient observations hands-free. These applications illustrate how speech recognition and generation can improve both clinical efficiency and patient experience. At the same time, they highlight the need for accuracy, privacy, and compliance with healthcare regulations, as mistakes or breaches carry high stakes. Education and accessibility also benefit from speech technologies. In classrooms, transcription tools provide real-time captions for students who are deaf or hard of hearing. Language learners use speech recognition to practice pronunciation and fluency, while text-to-speech helps with comprehension of reading materials. Accessibility tools read digital content aloud for visually impaired users or enable speech input for those unable to type. These applications emphasize the inclusive potential of speech AI, making knowledge and interaction more widely available. They show how technology can level barriers, ensuring that learning and communication are not limited by physical or linguistic constraints. For learners, education and accessibility highlight the human-centered impact of AI when applied thoughtfully. Emotion in speech AI is a growing research area aimed at making systems more sensitive and expressive. Recognition systems attempt to detect emotional cues in voice, identifying anger, joy, or sadness to adapt responses accordingly. Generation systems try to reproduce these emotions, making synthetic voices sound empathetic or enthusiastic rather than monotone. For example, a customer service bot might adjust its tone if it detects frustration in a caller's voice. While still imperfect, these efforts reflect the recognition that human communication carries emotional as well as informational content. Incorporating emotion into speech AI moves machines closer to natural interaction, though it also raises ethical questions about authenticity and manipulation. For learners, this area shows how subtle aspects of communication challenge AI to capture more than just words. Personalization in voice generation allows systems to adapt speech output to specific preferences or identities. Brands may design unique synthetic voices that reinforce their image, while individuals may choose voices that feel more familiar or expressive. Some systems even allow voice cloning, where a short recording of a person's voice can generate a synthetic version capable of reading any text. This creates opportunities for personalized interfaces, but also raises concerns about misuse. Personalization highlights the tension between customization and ethics, showing how powerful tools must be guided by responsibility. For learners, it demonstrates how AI moves beyond one-size-fits-all solutions, tailoring interaction to individual users while navigating complex social implications. Security risks have become an urgent topic in speech AI. Deepfake audio systems can mimic voices convincingly, enabling identity fraud or misinformation. Voice spoofing attacks may trick biometric systems, granting unauthorized access to accounts or devices. These risks underscore the importance of developing countermeasures such as liveness detection, watermarking, or authentication protocols. As speech AI grows more capable, its misuse becomes more plausible, requiring constant vigilance. For learners, security risks illustrate the dual nature of technology. Every advance that empowers can also be exploited. Understanding these risks is essential for building resilient systems and ensuring trust in AI-driven communication. Bias in speech recognition remains a serious challenge. Studies show that systems often perform better on speakers of certain accents, dialects, or demographic groups. These disparities arise when training data does not adequately represent linguistic diversity. The consequences can be exclusionary, frustrating users whose voices are misinterpreted more frequently. Addressing bias requires more inclusive datasets, careful evaluation, and ongoing refinement. The issue reflects a broader truth. AI systems inherit the limitations of their data. For learners, bias in speech recognition serves as a reminder that fairness is not automatic. It must be designed and tested deliberately to ensure speech technologies serve all users equitably. Privacy concerns also surround speech AI, particularly in always-on listening devices like smart speakers. These systems continuously monitor for wake words, raising questions about how much data is collected, stored, and shared. Users may worry about sensitive conversations being inadvertently recorded or misused. Companies face pressure to provide transparency and control, ensuring that data is handled responsibly. Privacy is not just a technical issue but a matter of trust. For learners, it emphasizes the ethical dimension of speech AI, creating systems that enhance communication without compromising security or autonomy. Responsible handling of voice data is critical to long-term acceptance of these technologies. Resource demands are another factor shaping speech AI. Training large models for recognition and generation requires immense computational power and vast datasets. These demands limit participation to organizations with significant resources and raise concerns about environmental impact. At the same time, researchers are exploring more efficient architectures and transfer learning techniques to reduce costs. Resource demands highlight the trade-off between scale and accessibility. For learners, they show that progress in speech AI is not only a matter of algorithmic innovation, but also of practical constraints balancing performance with efficiency to make systems sustainable and widely available. Speech AI is increasingly integrated with multimodal systems, combining voice with vision, text, and other sensory inputs. A voice assistant paired with a camera might not only respond to spoken commands, but also recognize gestures or interpret objects in its field of view. Multimodal integration allows for richer, more natural interaction, reflecting the way humans use multiple senses simultaneously. For example, a virtual tutor could explain a diagram aloud while highlighting parts of it visually. These systems illustrate the direction of AI toward more holistic understanding, where speech is one channel in a broader web of interaction. For learners, multimodal integration highlights the expanding scope of speech technologies as part of comprehensive AI experiences. Open-source speech frameworks have accelerated progress and broadened access. Toolkits like Caldi, DeepSpeech, and ESP.net provide researchers and developers with ready-made components for recognition and generation systems. These frameworks standardize methods, support experimentation, and foster collaboration. They lower barriers for individuals and smaller organizations, democratizing participation in speech AI development. By sharing tools openly, the community advances more quickly and builds systems that benefit from diverse contributions. For learners, open-source frameworks provide practical entry points, enabling hands-on experience with speech technologies and encouraging innovation beyond large corporate labs. The future of speech AI is likely to emphasize greater naturalness, adaptability, and security. Research is exploring models that not only transcribe words, but also understand meaning, emotion, and context at a deeper level. Efforts are being made to create voices that sound even more human, capable of expressing nuance across cultures and settings. Security measures are becoming more important to counter risks like deepfakes, while ethical considerations will shape how personalization and data use are handled. The ultimate goal is to create systems that are not just accurate but also trustworthy, inclusive, and context-aware. For learners, the trajectory of speech AI highlights its role as one of the most human-facing branches of AI, where progress directly shapes how we speak with and listen to machines. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.